So it's my distinct pleasure to introduce my colleague, April Galyardt, who is a machine research scientist for us here at the CERT Division. She's got a ton of experience in this area, and she's an excellent speaker, and so she's prepared a wonderful tutorial for you today. So I just want to introduce my colleague, April. Thank you.
So, thank you to those of you who are not already on the road. My background is a tiny bit different from most of the speakers that you've heard today. I'm a statistician and work in machine learning, but I came up focusing on applications in education and like computer tutorial systems where you've got students who are working on a computer and trying to learn things, and we're trying to learn things about what the students know from what we can see them click. And so this kind of brings us to, well, now what do we know about everybody else from what we see them click? And so I'm going to talk about record linkage a little bit and some of the ways that can kind of go wrong, and then that's going to lead us towards differential privacy. Just to get a show of hands, how many of you have heard of differential privacy before? Okay, good. I have picked the right topic. So record linkage in general. I have two databases. They're supposed to be about the same people. I need to match up the records in database A with the records in database B. And this is non-trivial. There's some complexity here. The formatting of the names, the formatting of the addresses, the formatting of the date of births. There's a lot of processing that has to go into this. This is a non-trivial task. But at this point, it's a pretty routine task. We've got textbook on it. We can teach undergrads how to do it. It's non-trivial, but routine at this point. In fact, I pulled these pictures straight out of such a textbook. And there's a good process for going through this. We do the pre-processing on both of them, so it makes our life a little bit easier. Then we can compare the records and review. But the process has become routine, and there's lots of different methods for comparing records. You can do a deterministic matching, you can do a probabilistic matching, so forth and so on. Now, a problem that a lot of us face is we need to share data for various reasons, or we need to share it with analysts. Since I was coming out of education, this was a problem that we faced a lot because we don't like to share private information about kids under 18. And so how do we anonymize this so we can share our data with other researchers? You think, okay, I delete the name, email address, that standard personally identifiable information. An IP address definitely falls in that category. Well, okay, so in 1997, this Group Insurance Commission released anonymized health records from Massachusetts. We're going to release them out into the world and let everybody do their data analysis, and we're going to learn all kinds of new things. And so they deleted what they thought was all the identifiable information from it. Now, a clever researcher took medical data and the voter data, two separate databases, and were able to match up records using zip code, birth date, and gender. And they were able to pull out the governors. They focused on the governor because he's already a political figure, and sometimes they release their medical records already. But only 6 people shared the birth date, only 3 of them were men, and he was the only one in his zip code. So now we have his medical data. Is it always that easy? So the Census Bureau was one of the first places to kind of deal with this problem, because it's their job to collect data about Americans, and they want to release as much of it as possible. And so earlier versions allowed you to look at a neighborhood level, and you could actually come in. So this is a map that I pulled off very recently, and it's only showing at the county level the percent American Indian and Alaska Native. And so you can see in that particular region of the country around the Alleghenies, those numbers are pretty small. If I plot those numbers on a city level, if I plot those numbers on a block by block level, I start to identify individual people. And so they realized very quickly, you can't do that. And so now only offer county level data. And they figured out that 53% of the population can be uniquely identified by place, gender, and date of birth. And if we make place a little more specific, turn that to zip code, that turns into 87% of the US population. So those three pieces of information, which we consider that phone book, that can be used to reveal things that we maybe wish we weren't revealing. Sure. Yeah, so if place is more at the city or state level, because like Pittsburgh's got, I don't know how many zip codes, at least 5. So zip code's a little bit more specific. So it's that easy to re-identify 87% of Americans. So how easy is it to re-identify people? If I wanted to, say, dox an entire police department, how easy would that be to automate? Piece of cake. I write a web crawler, I do a little bit of matching, I'm done. So this is exceptionally easy to do. But it goes a little bit beyond that. All right. This happened like 10 years ago, but let's review. Slightly more than that. So the Netflix prize. Netflix put out all of a big database of movie ratings. And they had a competition, kind of like the Kaggle competitions now. If you can write a better algorithm and make better predictions so that our customers get better recommendations for what movies they would like, you can have $1 million. And this was whoever's got the best algorithm wins. And so they ran this competition, and they ran it, I think, twice. Because what happened was that these two guys took the Netflix data, and they took the IMDb data. And first of all, if you pull in the IMDb data, you get much better predictions for what movies are good movies and what movies people will like. But you also get to map and identify people. Because if I watched a movie on October 3rd of year whatever, and Netflix knows that, and I sometime around then reviewed that movie on IMDb, now it's very easy to match those records. And in fact, the record of movies you watch is a fingerprint. And so if they had 2 movie ratings, just 2 movies, and dates accurate to about 3 days, they could get almost 70% of people. But if they had 8, they get almost everybody. And but notice 8 ratings, 2 of which might be just wrong. So this is exceptionally easy. So we were talking earlier about all your likes and things. You read a particular article, this is exactly the same. That's a fingerprint. It matches up. And you don't have to have your name attached to it for somebody to reattach your name to it. So we will try to make these slides. This presentation will go up later, but I've got some links here. The ones on the left are kind of the basics. There's Coursera things and Python toolkits on how to do record linkage. The Sweeney paper, that's the one where she pointed out, hey, this is kind of easy. But how do we do this right? And that's where differential privacy comes in and what the idea of differential privacy is. So what we want, this is a little more formal definition, but we want, if we're going to query a database, we want the answer that I get from the database to not depend too much on any one person in the database. And so we can operationalize this in terms of, I've got database A and B, and the only difference between them is that your information is in one of those databases. I would like any query I run on this to not depend so much on my answer that it gives away information about me. That the difference between, if I get an answer from A and I get an answer from B, if the only difference between those 2 answers is my data, you've now given away information about me. So we want, excuse me, We don't want that. So what do I mean by statistically equivalent answer? And the best analogy is if we kind of go back to like a Stat 101 idea. We want to know something about a population. For simplicity, let's say that number is just the population mean. If I take one sample, I get a sample mean, which I know is close to the truth within some error bounds. And if I took a different sample, I would get a different number, which is close to the truth within some error bounds. So I would like the difference between what I get from database A and what I get from database B to be about the same difference, so that it doesn't depend just on me. So this is the property we want. We want good information about the population and no too little information about individuals. Now, I want to make an aside here about machine learning and neural networks, because the sample mean doesn't give away too much about individuals. Although sums, if you have two sums, then you know the difference is just that one number. But we can add a little bit of noise to that. But a neural network, these guys, they took a corpus of documents and they inserted a phrase, the random number is, with 9 digits representing a social security number. And then they fit a language model, which is supposed to predict next tokens. So if there's a T, then there's a high probability that the next letter should be an H. And they trained their model for exactly one epoch, which just means they barely trained it. They didn't overtrain this. It is barely trained. And in 88 cases out of 100, they could recover that random number. So the moral here is, if information has gone into a neural network, you can probably pull that information back out. It doesn't really hide anything. And this is just unintentional memorization. If it gets adversarial, so this, for example, is if you have data and you have hired somebody else's machine learning, bought their product, but they have malintentions, and they want to steal as much of your data as possible. But they don't get to run and they don't get to see your data. They just get to see output, or they just get to see model parameters. Well, then there's different ways that they can do this. They can encode things in the model parameters. They can add extra model parameters, and they can recover all of the data. Or if they just have predictions, they can supplement a little bit of extra data and leak all the data. So if it's just, I want to see if I can pull out social security numbers, yeah, you can do that. Or if you want to pull out something more detailed and you're actually malicious, you can get whatever you want. So running things through a statistical model, all of the information is still there on the other side. So just because all you're releasing are model predictions doesn't mean you've achieved any privacy at all. So how do we achieve this? So the key idea is actually fairly old. It comes from a survey methodology. So imagine that you are a 1960s social scientist, and you would like the answers on average to some of these questions. Do you imagine that if you gave people a survey, you would get honest answers? Exactly. So they had to come up with a way where people would probably answer honestly. And so the methodology they came up with was this. You're going to have the participants flip a coin. And if they flip heads, you're going to give me your answer. And if you get tails, you're just going to say yes. That way, for the people who are saying yes, you don't know if they're answering, yes, I flipped a tails, or yes, I had an abortion. You don't know. So you've given your participants plausible deniability. And as a researcher, since you know that about half, it's a coin flip, right? So there's binomial distribution, but about half of your yeses are not true yeses. You can actually come back and estimate the correct answer, the true proportion of yeses, because it's math at this point. And so you can make this a little more complicated. You can say, we're going to flip a coin, and if it's heads, answer truthfully. If it's tails, flip another coin, and you can say yes or no. So what this is it's a noise generating process. We're adding understood noise that we can do the math on and calculate our standard errors and still get an estimate of the thing we actually want. And that's what this differential privacy algorithm does. This is Google's algorithm, which I could go and read the paper and, okay, this is what Google does. Apple, as of what I found, has not released their algorithm yet. If they did it, it was recent and I missed it. So we have a thing we want to encode. In this example, the number is 68. That's what we want to encode. That's what we want to save. That's what we want to include in our analysis. So the first step is we're going to run this through a Bloom filter and hash it. So we've reduced the number of bits, or if the string is longer, that's a reduction. Then we're going to generate a fake Bloom filter. This is our coin flip. So f is a tunable parameter. Notice if f is 1/2, then I report the correct answer with probability 1/2. And I'll say yes or no based on another coin flip. So this generation of line 3, the mouse works. The fake Bloom filter line. That's exactly our coin flipping process. So we flip one coin. If it's heads, we report the true bit. If it's tails, we're going to generate a random bit. And so this F probability is a tunable parameter, so I can save more of the true data or add more noise as I see fit. In their paper, they kept F at 1/2 so that it was just a coin flip. And then, but that's not what I'm going to send to the server yet. I'm going to flip some more coins. And so what's sent to the server is this S. And so if line 3 is a 1, I flip a coin with 1 probability, and I'll save a 1. If it's a 0, I'll flip another coin. And if it's, yes, Mark? Oh, no. So I've created 2 separate random numbers. Why are there 2 separate random numbers? Why do I need both of them? So the fake Bloom filter, the B prime, that stays on my device. That does not get sent to the server. Because if this is something, let's say it's a home address. I'm going to type my home address into like Google Maps pretty frequently, or even have it saved. So that's going to get transmitted fairly regularly. You're not. Pittsburgh traffic's a little unpredictable. Sometimes you want to know which bridge to take. So this B prime stays on my device, and this ensures that if somebody observes S repeatedly, they observe what gets sent to the server repeatedly, if they observe enough of those, they can average them out and go, oh, well, the truth must be this. The fact that there's this little extra bit of randomness in the B prime ensures that the average is still not my information. So this B prime produces long-term privacy. And then the S is producing more of a short-term extra randomness. So this makes a little bit of sense. And we're adding noise. We're adding noise in a very specific way. And the 2 different flavors give us 2 different kinds of privacy. So let's think about for a second when to privatize the data. So in some cases, if your data has to be recorded precisely, health records, I would like the doctor to not have a noisy example of my health records. I would like them to record that correctly. So in this case, I can apply a differential privacy algorithm before I share the data with the analyst. The doctor needs to see the truth. The data scientist, they can work with the average data, the noisy data. But a website search, does that need to be stored precisely? And in Google's case, no, they store the noisy bit so they can do the averaging. Because they've got enough data, they can average many, many things. So when you're doing this, we've already talked about in the panel, if you have data at rest, it should be encrypted. Maybe if you have data at rest, it should already be noised, unless you need it very precisely. Now, devil's in the details. If we go back to this, I've got 3 different tuning parameters right there. I've got the F, which governs the first coin flip, and then I've got a Q and a P, which govern other coin flips. And then I've got the Bloom filter itself, which is how many hash functions am I using. So there's a few tuning parameters here to deal with. And so, of course, the equations on how much information you're actually leaking every time you query depend on those tuning parameters. And this is true not just of Google's algorithm, but differential privacy algorithms in general. The more you're going to ask and the more you're going to query the database, the more noise you need to inject to ensure privacy. And once the data has leaked, it's gone. So if somebody has seen different evaluations of something, and they can average it, and now they've got the same answer you have. So the devil's always in the details. If you don't add enough noise, you leak sensitive data. If you add too much, you might just have noise. So you don't want to erase all the information. And I've linked here to this blog here on the Getting Started side. It's very good, it's very clear. And then some of the resources on the other side, the one at the bottom is actually Google's algorithm. They have made it public and put it up on GitHub. Apparently I talk very fast. So one of the points I want to make here is data can be made privacy aware and still be useful at the same time. We don't have to choose one or the other. We do have to be careful about having both, but we can have both. We can downsize data. We can take a subset, and it can remain useful. And you can still perform the ML and analysis on the differential privately data. In fact, given what I just said about some of the ML algorithms and the neural networks preserving information you didn't really want them to preserve, it's probably better to go ahead and privatize the data before you run the neural network. And then this isn't the only this is not the only way that privacy problems can arise. Another problem that comes up a fair bit is if you have a bunch of people who have similar data and nobody wants to share or nobody can share, then you can do something called secure multi-party computation. And that is, you compute your answer, report back, you compute your answer, report back, and then we can synthesize the answers. And when I made this, I did not know this was going to be the theme for the day. But I think this kind of sums up a lot of what everybody has said today, which is data is an asset in the same way that gunpowder was an asset on a frigate. That is, you can't fire your cannons without it, but if you don't take care of it, things explode, or it gets wet and doesn't work. So that's what I have. And
yes, so question. So you mentioned use of a hash in connection with the Bloom filter. So I guess in one sense, this approach is kind of like homomorphic encryption except for data, but it's not as good because it's using a hash. Is that a good understanding?
I think that's a fair characterization. That because you've hashed it and then you started flipping coins, you've lost a little bit of information. Yes, you can, at least on average, you can reverse it. I believe they had to observe 10,000 observations in order to get back a population distribution, and even then it was just information about the population. all information about individuals was false. Yes. That trade-off is certainly true. And that's why I kind of came back to here, was that calculating that confidence error is very simple for the mean, but you're adding noise, and how much information you can still recover. It depends on your sample size. It depends on, in the case of Google's algorithm, how long the strings are that you want to encode. They did calculations showing if it's not something I'm going to need to use again and again and again, and I can just do that instantaneous and not need that second layer of coin flipping, of course you need much less data. And this is a standard. It's a standard problem. That trade-off is always there, and it's always kind of specific to your case. Yeah, and that's very much going to depend on your use case. If you're talking, Google searches, they've always got new samples coming in, and they can kind of start their database over. If you're talking about health records, you definitely don't want to add too much noise, because you don't want your algorithm to start killing people. So, what was that? That would be bad. There's in the blog post that I linked to, they actually talk about a paper that people had looked at health records, and when they added too much noise, it was getting the dosage wrong, and it was actually recommending dosage levels that could be lethal. And so, yes, there is a very real trade-off in terms of how much noise to add and what your particular application is. Right. Absolutely. Yes. So there were earlier versions to achieve this differential privacy where they were designed for quantitative variables, because if all you're collecting is a mean and that's all you need, then you can add a tiny random number that's less than your standard error and retain basically all the information, and that's relatively easy. What Google's algorithm did that, if it was not the first, it was almost the first, was they were working with categorical variables and strings and things that were not just a number, where they could add noise to these more difficult things to store. Does that answer your question? Sort of. Yeah. Well, no. This algorithm does work for discrete variables. Adding small normal noise is what only works for continuous.
But to your point, it gets a little difficult to figure out. It requires an expert to understand what information you're looking to retain and what information are we okay having uncertainty surround. And to that extent, once I've come to that conclusion, now I have to figure out how do I use something such as this hashing algorithm or whatever to to store the data in such a way that I am able to add the noise you're referring to. So the example that we gave earlier with the, have you used heroin, right? That's a yes or no, right? That is a categorical, and you can figure out, have you used any of these drugs and come up with that sort of thing and store it in that context. And there are honestly ways of turning categorical into numerical values. But all that comes back to is you can use these kinds of approach even with that kind of data.
Thank you, Ellie.
Yes. That's exactly the point. And for those of us familiar with databases, it's a little bit uncomfortable. What do you mean I'm querying the database and getting back a wrong answer? Right? That the whole point of keeping a database is I get the right answer. No, you are specifically losing information to gain the benefit of privacy for the end users. And honestly, to what we're talking about before, risk mitigation for yourself. You may not want to store all the raw data because that may expose you to liability you don't want to hold. So now when someone comes to you and says, show me all your users who have this particular property, make it up based on your favorite law enforcement case, you can legitimately say, I do not know because my data does not contain that.
Lena? Nope, you're good. Okay.
I would say a little differently. So think of it this way. When Google to use Google because they do this a lot, when Google releases a new feature in Gmail, their question is, are users using this feature? Or how frequently do they use it? Or how well are they using it? They don't care if you're using it. Traditionally, we would think, in order to know how well everyone's using it, I have to store how well you're using it. What this allows them to do is store overall how well everyone's using it without storing how well you're using it. And that particular capability gives them the benefit of the answer without the liability of the data. And that it's in all these contexts. I want to know what the prevalence of AIDS is in the population. I don't want to know if you have AIDS because, frankly, you don't want to tell me, and it's a risk for me to even have that information. This allows me to know the population, but not know the individual. The situation can definitely arise. I am not a lawyer. She is not a lawyer. This is not legal advice. You need to follow regulatory requirements. So if an example of the bank we're talking about, if the bank requires someone to keep a record for all individuals, clearly this technique will not apply. Right? You can only use this in the area where you are allowed to not store the data. Saying to someone, well, I'm using differential privacies, I can't give it to you, they could be like, tough luck, you're still going to jail. And
right. Well, that's why I think, his example of the bank needs to keep accurate records for some purposes. The marketing people don't need those records. And so before you share your data with marketing, that's when it happens. And so that when should it happen is a critical question kind of across the board. The police need accurate records. They don't necessarily need to share 100% accurate with everybody else, particularly with the juveniles. This one? Okay. So this is kind of translating this jargon that's used in some of the part of the language issues in this area come from a lot of the work is being done by computer scientists who speak one way, and a lot of the work is being done by statisticians who speak another way. And so I'm trying to translate here between the two languages. So this idea is actually a Stat 101 idea. It's the idea of a standard error. That I know that if I take a random sample, I'm going to get an answer that is close to the truth. And so, and that's what differential privacy is trying to do. It's trying to give me the same uncertainty that I would get from a random sample, more or less. Right, and that's, I have exactly the same doubts about how well the methodology worked there, but you know, at that point in time, it was the best we could do to not get 100% no's. And so any estimates then I would tend to gauge are still underestimates because of exactly that problem, and the experimenter there should not be the one flipping the coin because then they know. And so, yes, back then it was kind of in the better than nothing category, whereas here, because it's all within the database system, it works a lot better now. I think that's an interesting idea, and I would love to see how the numbers would differ. But there's, when dealing with people and surveys and social science kind of stuff, the other thing I worry about in that particular case is the self-deception aspect of, oh yeah, we totally do that. No, you don't. So how much those two things play together, those are very hard things to estimate. That's self-report surveys always have that problem.
Thank you very much, April.